seems to be kind of a more general thing than just for version control. So given a very short insight about to do the basic operation of SSP that we did last year. And now we dig a little bit more into the internals. We had students work with this, implement some broadcast abstraction on top of Git for a course, and we plan to look at it a bit more and then try to solve a bit of the issues we had with SSP. So now I'm in the process of working with students to try to re-implement some of the application we did to see and compare side by side what it looks like. So that's a bit of the direction which we're going. And Ali was a teaching assistant for the course and had to learn Git and Bash and all that stuff really quickly in order to teach it to students. And now that he ramped up on all that technical knowledge, I offered him to do a presentation on Git on these things in practice, presenting the QBells. So that's how we came to this.
Yeah.
So with this, I'll let you.
Thank you.
Give the presentation.
Let me start Git internal. So hello again to everyone. Welcome to this talk. I'm going to talk about Git internals, and I'm a PhD student in Professor Julian's group, and let's get started. My agenda is very simple and basic. I'm going to separate the entire talk in two parts. In the first part, I'm going to talk very quickly about general structure. And in the second part, I'm going to build a repository from scratch and see how we can use Git plumbing instructions or low-level instructions to build a repository from an empty folder. So let's dive into the first part. I'm sure that all of you are familiar with Git, and you know that obviously it is a version control. From my perspective, and our purpose Eric mentioned, Git is nothing more than some objects plus some pointers or references. And using these two types of items, you can create a graph structure like the one you see in the picture on a non-volatile memory. So it means that whenever and wherever you need such structure, on a non-volatile memory, you can use Git, and on top of Git, you can build your application. So if you need any sort of graph structure like this, you can benefit from Git. And the thing is that you have different objects. They can point to each other. Generally, you can create a graph, and you can store some pointers which can point to any of these objects. Eric has some ideas and some applications, and if you are interested, you can talk with him and get more information.
First question, it's okay if you say that later, but are the pointers here in red in any way different than the pointers in black, or is it just that some of the nodes also have pointers?
No, it doesn't something special. It's not something special. I just wanted to say that okay, I can store this pointer. We will see that what is this pointer, and you can store it somewhere. And then when you want to find this node, you can use this pointer. Okay. Cool. I said that we have two types of items. One is objects and the other is pointers. What is an object in general in Git infrastructure? All objects are nothing more than files. Okay, but there are three different types of objects: blobs, trees, and commits. And based on their content, we can categorize these three types of items. And I will introduce these three types of items. But one thing which is very important now for this slide is that the naming scheme for all of these objects is the same. And when you want to name one object in Git infrastructure, you have to calculate SHA-1 hash of its content and this SHA-1 hash is the name for that object or that file. So here, for example, you can see that I have one file with this content, and SHA-1 hash for this content is something like this. It is longer, but here I just wrote some part of it. And this SHA-1 hash is its name. So this object could be a block, a tree, or a commit, but this SHA-1 hash of this content is its name. Okay, and these SHA-1 hashes play a very important role in entire Git. Why? Because a SHA-1 hash is a pointer. So object is this file, and its SHA-1 hash is the pointer. And you see these pointers everywhere, like in data fields for some objects like trees and commits, and also in some simple files like what you will see in branches. Actually, a branch is nothing more than a file which contains one SHA-1 hash. Okay, so branches are very simple. This is a branch. This is also a branch because it's just a pointer. Okay, let's continue with different types of objects. As I already mentioned, we have three types of objects. The first type and the simplest one is blob, which is short form of binary large objects. And as its name suggests, a binary large object is like a buffer. When you want to store your data, you put your data without any metadata like timestamp or name or something like this into your blob object. Okay, it is just like a buffer. You put your data in blobs, and it just holds your data, not any sort of pointer or SHA-1 hashes. It is just your data. So see blobs as buffers, for example, in programming languages, for example. Okay, the second type of Git objects is trees. A tree is a collection of these SHA-1 hashes, which means that it's a container for your pointers. For example, here you can see that we have these objects with this SHA-1 hash, which has this pointers inside of that. You can see this is a blob with this SHA-1 hash, this is a tree with this SHA-1 hash, and etc. So it has some pointers to different objects. Which type of objects? Just two types of objects, blobs and other trees. And something interesting is that here you have another field, which is a human readable name. Okay, then it means that using trees, you can assign human readable names to your blobs or other trees. Okay, then having these two types of items, these two types of objects, you can create a file system with these two types of objects. The third type of Git object is commit objects. A commit wants to snapshot our current state and has the following fields. It has some metadata, like when you want to commit something, you say, this is my message, I'm the author of this commit, and things like this. You have a parent for your current commit, which could be one parent, or you can have multiple parents. So you have to put some pointers here to point to other commits. So here, in this field, we can put some pointers as pointer to other commits. And we have another field here, which is just one pointer, just one. This could be multiple, but this one is one SHA-1 hash or pointer to one tree. And here, the point is that this SHA-1 hash can point to a tree, that this tree snapshot our current state. How? We have something like 3 blobs as our data, I don't know, 2 trees as our folders or directories or everything. We can refer to them here by listing the pointers and then put this SHA-1 hash here to say that this is my current state. So using this field, we can capture our final state, our current state. Okay, here there is a field for capturing state, and here there is a field for talking about our updates. Anyway, let's see this example, which is very simple. We have one commit. This commit has this field as its tree, and this tree says that we had one blob with this name, and this is its hash, which points to this blob. And we can see that the content is something. And again, we have another tree, which we can see it as a folder, for example. This folder contains this folder and this blob. This blob is, the name is this one and the content is here, and this folder is this one, which contains another blob with this content. Again, here we can see that for the first commit, we have one tree, and this tree captures this state. In this state, we had just one blob with this content, something. And the other one, the other commit, has another tree with this file and this file, or this blob and this blob. But as you see here, we have the same blob for this tree. But why this tree is not the same with this tree? Yeah.
It also has the other class.
Yeah.
So it has 2 objects in the tree.
Yeah, and because the content is changing, its SHA-1 hash will change, then it means that we need another tree. Okay, I think that's enough for theoretical part. So let's dive into the second part and try to build a repository from scratch.
I have a question.
Yeah.
Did you simplify this in any way? No, because like.
Yeah.
Okay, so then specifically, the current state doesn't stay materialized for every commit, right? It mostly deals in.
When I say state,
No.
So like if I have a 1 megabyte text file and then I make one
Yes.
character change, I will
Yeah.
materialize 2 different files in this.
Yes. You also have to always recompute the diff between 2 comments.
Okay, I would.
That's why it is not recommended to store like random base or very large binary data.
Okay, so it's just because they're not super random to begin.
No, it's going to, like whenever you change it, it's going to put another 100 megabyte file.
Okay, yeah.
Not what it was made for. Anyway, sorry.
no problem. So creating a new repository is as simple as you see here. You have to just create one empty folder with that git name, and inside this folder, you just need 2 subfolders. One, because we have 2 types of items, objects and references or pointers, we need 2 objects. The folder objects stores all of our blobs, trees, and commits, and the other folder under subfolder head, you can see all of your pointers for all of your branches. And then we need a file called head to say to get that what is my current pointer or what is my current branch. Okay, then easily when you do that, you can create an empty repository. Let's do that. Test. I create an empty folder test here, then inside that, I create.
I did check directly now.
Yeah, I didn't do that.
Oh, yes, it needs to be within the text.
Yeah, sorry. And here I have this one. This folder stores my objects and refs stores my references, and inside that I need heads. We have in like real life versions, you can see inside refs we have different types of folders like removes, heads, and other things. But I don't want to go deeper and just want to work with local. So here and we need also.
So is your main and then the.
Yes. Echo ref, our reference is into refs, heads, and let's have one name for that. Generally, people use main for their main branch. We can use another way, but be compatible. Okay, into git head. As you see, we have just this file, this folder, and this folder. And if I say git status, it says, yeah, no comments yet, but let me tell you this. Yeah.
No, you really have to take.
Git status and nothing to comment. Okay, so it is very easy to create an empty repository. For the rest of the talk, I'm going to use this color boxes for different purposes. The first one is working directory. When I want to create a file, I'll put some icons here. That means that I have this file here. Repository is for commits. Index is used for objects which are in staging area, and and objects for database is all of our objects, trees, blobs, and comments. And as you see here, this head is the file I just created, and it now we said that our reference is an object of main with some hash which we have not created yet. Okay, for the first part, I'm going to create a file a.txt with the content of hello, and I want to commit it with the message commit one. So let's do that. So at first we have to create a file with this content. Nothing strange. Echo hello a.txt. Yeah. And now we put our file into our working directory. Then, because this file is my data, I have to create a blob for that to put it on Git database. Okay, so I have to read content of this file using cat, and then I have to ask from Git hash object command to read this data and put it on the database. So I pipe these two operations together. So cat a.txt git hash object dash std, which means that read from input and put it on your database. And as you see, as a return, I can see a line hash number, which is SHA-1 hash of this a.txt. Okay. Now, this file is also in my database. Okay, we can. There is a Git command. Using this command, I can list my database and see all of different objects in my database. And I can use an alias for it because I'm going to use it a lot. So let me do it. Show objects. Okay. You can check. Okay, then if I say show objects, yeah. Till now we have just one block with the size of with this SHA-1 hash.
The git hash object is
Basically,
basically just a SHA-1 hash and then copying the file into the corresponding.
yeah, if you here, if you use this command, it reads from here, and if you use -w, it's right on the database. But if you just want the hash SHA-1 hash of this file, for example, you don't use -w. Okay. Then the next step is to index our file. We have to put it on staging area. To do that, we use git update index with these arguments. It is just a number to say something about the file type and things like that, and I don't want to confuse you with this one. Okay, so let's do that. Git update index -- add cache info and I want to put this SHA-1 hash into my index with this name a.txt. Okay, then if I again show objects, what we'll see? Just one object, because I just put this object into indexing area, okay? Staging area. I didn't create any new object. Okay.
Maybe you can do git status and show that it is.
Yeah.
Staging.
Yeah.
Okay.
This is the next step.
Okay.
And if I say git status, you can see that yes, this file is really in my stage.
So where does it live right now on disk? Like where does this information that there is a new file in the index, where does that live?
Yeah, there is different files. One is that blob object, which is here. I can show you. Objects, you can see it. We say I said all of objects are stored here in the objects, and you see here CE something and this file. Okay, and if you see this SHA-1 hash starts with CE. Okay.
I think it's in the index file. That was one double layer.
But
This one,
yeah,
yes.
everything. What it is slow? Everything you put in your index is stored here, and obviously there is another thing which is your working directory. Okay, you have three types of things to do. Okay, then if you remember, if we want to commit something on Git. On commit object, we had three different builds. Let me get back. Yeah, here we had one tree, parent, and other information. So we need one tree to take snapshots. Okay. So before commit everything, we need one tree. Using git write tree, I can create this tree. So git write tree, take a snapshot from my index and create an object based on that state, and this is its SHA-1 hash. And if I say show objects, you can see that now I have two different objects. The first one is my block, and the second one is this tree, which snapshots our state. And I can ask from Git to show me the content. If I show the content of block, you see the content is hello, and if I show this one, you can see that the type is tree and it contains a.txt. Okay, the next step is to create a commit and put it into repository. Using this syntax and this command, git commit tree, we can do that. Git commit tree. As the name suggests, we are committing a tree, and it is very interesting for me that you are committing a state, and the state is a tree. Oh, we need SHA-1 hash, so show objects.
What's the 33 here?
The size of it.
Yeah. The tree, which tree, this tree. And with dash m, commit 1, I think. Yeah, and if I have a parent, I can use like dash p and SHA-1 for that. And here you can see I created a commit object, and if I say indeed show, show objects, you can see that now I have three objects: one block with content of hello, one tree with content of a.txt, and the other thing is that this commit with a lot of information. Show, and this is the information stored on this commit object. Okay, my code is last slide.
Because you didn't set your email or something?
Yeah.
For sure.
And your name or your family name is maybe shorter than mine. Okay.
So this,
And
the commit is also stored in the object-db. This, like what we just got as standard output is probably already a parsed version of the commit description. Is it like, is that human readable if you open
Which one?
No, it's a binary format, you can open
Okay,
it. There's
fine.
no-
Yeah, everything's
Yeah.
to compress to work.
A6, this one is the commit. Yeah.
it? Not super helpful, yeah. Okay.
Okay, and as you see here, all of objects are here in my database. And let me just ask from git status. Oops, what happened? We have created an object, a commit object, but it says that, oh no, you have always a.txt, we did not commit it yet.
Your head is still pointing at nothing.
Yeah, exactly. If you remember here, we had this head which holds our branch pointer, and it says that our branch is under refs heads main. So let's go and see refs heads. Oops, nothing. I don't have main yet. So let's create it. And it needs a pointer to a block, a tree, or a commit.
It's a question.
Yeah. A commit, yeah. So I need this SHA-1 hash. Echo this into git heads, git refs heads main. Cool. Git the status. Yeah, we comment our first. And if I say git log, you can see that yes, we have head is pointing to main, and this is our first commit. Okay.
Are you going to talk about replication between repositories, like with push and pull?
I don't know.
Okay.
Okay, so let's see what is a branch. As I already said, a branch is nothing just a pointer in a file. Okay, so let's do that. Let me git show objects again, and I want to create another branch with this way, echo this into git reps heads and feature one. Okay, I created just a new file here. You can see I had this one with this content. I just copy it and rename it as feature one. Then let's ask git log again. Oops, cool. We have two branches now. And what if I want to switch to the other branch?
You update the head from.
Yeah, exactly. Head is pointing to main. I just have to update head. Okay, let's do that. Head feature one. And then ask again. Yes, now head is pointing to feature one.
But I can also point head directly at a commit if I want, right? That's then the detached head that you get warnings all over the place.
Yes.
Yeah.
Okay.
Okay. And the interesting part for me, at least, is that what if I want to modify a.txt? Can I modify the blob object which is related to a.txt? Let me show objects again. We have this file, which is equivalent to a.txt on my database. Okay, can I update this and say, let me show you the content? Can I update this file and write something else here, like hello world and everything is fine?
You mean modifying the object in the Git database
Yeah.
that way?
Things will go wrong as soon as you try to transfer anything also, like.
Mhm.
I don't know if Git
But-
checks on
when I want
everything all the time, but as soon as you try to send that to someone, they're going to check the hash.
Yeah, and when I modify this file, the hash is changing. Okay, then there are many files, like here we have just the 1 tree, but in general there are other files that are pointing to this file, so logically it's impossible. And let's see what will happen in Git. Okay, I'm going to I create a new repository with the name of auto and use its high-level instruction. So I create a Git repository. I want to echo hello a.txt, and I say git add, not that way, very simple way, a.txt and git commits -m. Let's say again commit one, and git log. You can see everything works fine. And I'm going to modify this file. Hello. And now if I say get status, it says that A is modified, and I'm going to git add A and git commit two. Okay. Done. Git log and everything is fine. Now, let's see what is inside this new repository. Show gits, show objects, excuse me. Cool. Let me make some space. As you see, we have two commits, obviously, and we have two logs and two trees. Okay, so it means that when you want to modify your file, blobs are not modified. You completely working with another blob. This blob is 6 byte. With the content of hello, and the other one is this one. Hello. Okay. Then let's see what's inside these trees. It shows, and both of them have the same size. Okay, this one is just a.txt inside, and the other one, 2e is 57. Yes. And this one is also a.txt. So why I have two separate trees for the same file? Yes. Here, it is like this a.txt is different from this a.txt, and in real objects, Git doesn't store a.txt. It stores its pointer, so it is hashed to this blob. So this is stored inside this tree, and this a.txt is this SHA-1 hash. So these are different. So we need two different trees, two different snapshots. Okay. It is, and let's do it in this way. I just want to copy all of this. Oh no, I cannot copy. So if I get back to our first repository, cd test, we can modify our a.txt echo word. And now then capture a.txt and create a blob for that. Git hash object, and was the syntax of it is cdin -w, and then update state, update index dash add.
There's a typo in the update.
This object again with a.txt.
What is the caching block for again?
This you can talk about different things. I'm not very familiar with this information, but this says that what kind of object you are creating.
The access control actually.
Yeah.
The 644.
Yeah. There's only 3 different types of file that Git supports, so it doesn't support the full permission system of Linux, and the file don't map to this, and the other 2 I don't. But might be executable.
I
Yeah,
do.
that's the 644.
So when you get a repo, you don't actually, I think, get any permission with this. So like the permissions are cached locally. I think this is what this is. I don't think Git stores permissions, or I don't know.
It does.
It does. Where
Yeah,
like,
when you have a file in your Git repository and you make it executable, it will
but it
go
caches
outside
it,
the-
no, but it caches it locally for you. But if you get a repo from someone from GitHub, for example, it doesn't come with someone else's permission, right?
Yeah, I think if it's a subset, it's supported, I think executability is supported as well.
Okay.
It's super unpractical.
Okay, so I don't, I'm maybe someone make a test, create a file, commit it, and then make it executable and see if something changes, and you can commit that. I don't think so.
Yeah, but I don't think it exchanges the, like the user IDs and stuff like that, that's not in there.
Okay, I will like experiment with it, actually.
Yeah, no problem. Okay, till now, I create, I modify, in my, handy GitHub, Git repository, I modify a.txt, I can word to that, and then I create a hash object, a blob for that here, then I add it to my index here, then I create a tree for that, actually I take a snapshot, and then I created a commit, which is here, git commit tree. This tree is my snapshot in tree, and here my message is commit to, and I said that I have a parent for this commit with this SHA-1 hash, okay? So, but is there any problem here? Git log. Oh, I created a commit, but it's still not here in GitLab. What is the problem?
You didn't update feature 1.0.
Yes, exactly. This is, as you see, there are two rows. You have to be careful for all of them. One is for your objects and your database. The other is for your pointers and where your branch is pointing to. So I have to update. Let me copy this. I have to update that. Echo.
I want to comment that it does store permissions apparently, because I wanted to recommit it, and it said that mode's changed.
Okay,
I thought it's just a local cache. So I was perhaps.
but there's some permission, it's not storing, I can think.
I think it only supports executability.
There was a five, like in this case, there was a number with 5 digits in it, and
Yeah.
it wanted to change that number, so it stores that all read write like executable flags apparently.
Okay.
Yeah, this one is correct. I got it wrong. Hash number. It drives as whichever. And now if I say git log, you can see that I have two different methods.
And so that's essentially the situation you were in just a second ago is what happens if I stupidly delete my feature branch and then check out some other branch and basically,
No.
or if I make commits on a detached table, for example, I
Yeah,
have
for
commits
example.
and trees that are not referenced by anything, so they're hard to find, but they're
Yeah.
in the database.
Yeah, for example, here I can go to refs and delete main, for example. Okay, then say git log. I have just this feature one. Okay, and if I do it like this is more interesting, I think. Git log. You have this file head, which is pointing to nothing. Okay, but if I say main, I just commit once. But what happened? Why I have just commit one? Let me show objects. Everything is in my database, but I can see just this commit one.
Main is still pointing at that
Yeah.
whole commit.
Main is just pointing to this commit, maybe, or this one. I don't know which is which one.
The shorter one that doesn't have a parent.
Yeah, exactly. Then it is. So I can update that with me. Here, feature one energy. Yeah. we can actually create any type of relationship between our commits. Maybe it's somehow stupid to have a relation like this I put here, but it is possible. You have some objects and they can point to each other. Okay, here, if I have time, no. Here.
Are you saying that they cannot mutually point to each other?
Yeah, your pointer can be like this.
But it cannot point back.
But like you can create pointers like this, or maybe more complicated.
Yes, yes.
Between commits,
Yeah, between comments you can create any sort of relationship.
but you cannot point back because you will have to solve the pre-image problem for the hash of the commit.
Yeah. And yes, that's enough, I think. You can create any sort of relationship between these items, and I wanted to say that Git is not only just a version control. You can create any sort of relation between your object. You can create a database and some pointers, and you can store your you can store some pointers to any of these objects and then update your snapshot based on these pointers. Okay, thank you for your.
Are you gonna write like a blog post about your way that is?
Sorry, I'm not very good in listening English. Would you please?
Oh, sorry, I apologize. Are you going to write a blog post about what you did?
Yeah, it's possible.
Be a good reason.
Yeah.
You see a lot of people, I mean, the Git is so popular and so few people understand how it works. It's great to have material like that up there.
Sure.
So I have a few things that you didn't have time to cover in your presentation. One thing that I find really interesting with this, because let's say in SFP we have a separate protocol for blobs. So we have a push protocol to put blobs randomly to a certain number of replicas. But yet you can push or pull any objects. Like we're used to pushing or pulling branches, but you can explicitly mention an object by @ and push that to another repository, and then it will be replicated. So it doesn't need a separate. It doesn't have a separate interface or a completely separate replication protocol for that. And when you're putting the branches and replicating with references, it will figure out the diff of the objects that one database doesn't have compared to the others, and only push those. And it does that transitively through the object graph, including the commits, the trees, and the blobs, for that to work. But you could use it at a lower level. You could build something else on top of directly the blobs if you wanted to. Yes.
Since it's been a year since I listened to you talking about FSP, could you remind me, like, how did you map at the time the kind of like feeds and profile information, this kind of like points to the Git concepts?
So the branch names were the public IDs of participants. So the public key then becomes self-certifying because when you sign the commit messages, you sign with your private key, and then you can check that back against the branch that you're pushing. So you can check that the reference is consistent with the commits that are underneath. And I was assuming that you had a single branch per participant. So then that's the way we do the Apinon logs. And now the paper that I wrote this year about BFT logs was about how to handle as a CRDT if you have a complex. If you're forking your log, but how do you deal with that? Then you replicate all the forks, and then you store proof pointing at the immediate commits, at the first few commits of each fork, as a proof that indeed the log was forked. And this way, since it's just Git and commits and everything, and you can replicate that, then you don't run into the problem with SSP where if you fork your log, then you have a partition of the replicas, and you cannot do anything anymore afterwards.
Okay, thank you again.